Alright, so this begins prequel 3, which is on permutations. Permutations are a very important example, and we'll talk more about the history of that maybe next lecture. But for now, I'm just going to try to explain to you the basic idea of a permutation, in particular, a permutation on the set of numbers 1 through n. Alright, so there's a more general concept of permutation, but for this lecture, we're just going to be talking about permutations of the numbers 1 through n. Alright, and what is a permutation of the number 1 through n? Well, it is simply a bijection. That is a one-to-one and onto map from 1 through n to 1 through n. So one-to-one correspondences, perhaps you might have called them before. But instead of bijections on the numbers 1 through n, if you take the set of all of these bijections on the numbers 1 through n, then that's what we call the symmetric group. Alright, so the symmetric group, which is just a label for us at the moment. Of course, we'll define group properly in the next lecture. So again, this is just a label at the moment. We haven't defined group yet. You didn't miss it. We just haven't defined it yet. I'm just calling a spade a spade. So we're going to learn it's a group. And what it is it's the set of bijections on the numbers 1 through n. Okay, so let's just get into it then. So here's a relatively simple example. N equals to 2. There are just two things in the symmetric group on two symbols. There's the identity map and there's alpha, where alpha of x is either equal to 2 if x is equal to 1, or it's equal to 1 if x is equal to 2. So this permutation sends 1 to 2 and it sends 2 to 1. Right? And you can calculate that if you compose alpha with itself, which is the quote-unquote multiplication for this group, right, whatever that means. But if we compose alpha with itself, we get the identity, since if you do it, here it is. I mean, if I feed it 1, we get alpha of 1, which is alpha of 2, which is 1 again. So 1 maps to 1, and also 2 maps to 2. So as you can see, alpha composed with alpha is just the identity map again. Alright, so the symmetric group on two symbols is not particularly interesting. But now is as good a time as any to introduce some language. If we have a permutation, alpha and Sn, then alpha fixes I if alpha of I is equal to I. Alright. In contrast, alpha moves I if alpha of I is not equal to I. So in my previous example, that the alpha we were just talking about, it moved both 1 and 2. Alright? Nothing was fixed under that one. Alright, but let's go on so we can see that more. We're going to be talking about moving and fixing throughout this whole talk, so let's just go on here. So obviously the notation I used in example 1.33 was kind of a drag, and so there's a better notation, which is the so-called array notation. And so suppose we were looking at n equals to 3, permutation on 3 elements, and let's look at the permutation defined by sending 1 to 2, 2 to 3, and 3 to 1. Right? You know, I guess in maybe back in pre-calculus or something, you might have written something like this: 1, 2, 3, 1, 2, 3, right? And alpha is what? It sends 1 to 2. It sends what? 2 to 3. And it sends 3 to 1. So here'd be another picture that you could draw to describe the permutation. But that picture maybe is not quite as efficient as this array, right? So this array is another way of writing the picture, or writing this string of three equalities thing, to try to say that 1 goes to 2, 2 goes to 3, 3 goes to 1. The inputs are the first row, the outputs are the second row. Alright, that's the array notation. Oh my goodness. And then S3 actually has 6 different bijections in it. And here's the array notation for those 6 different bijections, right? By the way, the alpha, which is written here, it moves 1, it moves 2, it moves 3, right? But as we look at this list of permutations, the first one here, it fixes 1, it fixes 2, it fixes 3. In fact, this is the array notation for the identity permutation in S3. If we look, let's see here, look for an interesting one. Here, this one. If we look at, I'll make it purple. If we look at this guy right here, it's moving 1 and 3, right? It moves 1 and 3. 1 goes to 3, 3 goes to 1, but it fixes 2. All right. So even this array notation is, it's okay, but the cycle notation is the winner. All right, cycle notation is just way, way more efficient, both for calculation and for many ideas about permutations. We definitely want to learn cycle notation. In fact, that's the main goal of this talk, is to make sure that you leave it knowing what cycle notation is and why it makes sense. So, in particular, make sure you can see both of these before I rattle on. All right, yeah. Okay, so this is cycle notation. So this 1, 2, 3 means that 1 goes to 2. As you can see, 1 goes to 2, right? 2 goes to 3. 2 goes to 3. And then it loops back, all right? So like this 3, where does it go? 3 goes back to 1. As you can, 3 goes to 1, right? On the other hand, this one, 1 goes to 3. 2 goes to 1. The 2 goes to 1 is seen from that 2 looping back to the start, right? So the cycle notation works like that. Let's see, 3 goes to 2, so you put in 3, it spits to 2, like that. So here it is in, here's a definition, if you like. If we say alpha is equal to ABC, what's that mean? That means that alpha of A is equal to B, alpha of B is equal to C, and alpha of C is equal to A. All right, there you go. That's a definition for what's called a 3 cycle here. All right. So cycles are read from left to right, and then they loop back. And there's ambiguity in the cycle notation. I mean, there's no ambiguity in the array notation. You got to give it that, right? No ambiguity. In other words, if we insist that the top row in the array be written in order, then the next row unambiguously defines the cycle. And there's just one array that that defines permutation, and there's just one array for each permutation in the array notation. In contrast, in cycle notation, there's an ambiguity. See, this cycle 1, 2, 3 is the same as that cycle 2, 3, 1 is the same as that cycle 3, 1, 2. All right, like think about if I plug in 1, 1 goes to 2 for that one, right? Looking at the middle one, if I plug in 1, it loops back, it goes to 2. If I plug in 1 to this one, 1 goes to 2, right? What happens if I plug in 2? 2 goes to 3. Plug in 2, 2 goes to 3. Plug in 2, 2 loops back to 3. So we've established 2 goes to 3 in this one, and that one. And we established that 1 goes to 2 in this one, and that one. All right, I guess one more thing to go. What happens with 3? 3 loops back to 1, 3 goes to 1, 3 goes to 1. So as you can see, this cycle notation, that cycle notation, that cycle notation, they all describe the same permutation, right? Or you can go back to the green box and look at it that way. And that really is what I'm using when I'm saying this loop back, blah, blah, blah stuff. Anyway, my point is to you, the cycle notation is not unique, all right? We can take a given permutation, and there may be more than one set of numbers which gives you the same cycle. And that's okay, because it's basically, another way to think about the cycle is like a loop. I don't think I have this in the notes because, well, I'm not that good at tech. So we could think 1, 2, 3 is literally a loop, right, like that. 1 goes to 2, 2 goes to 3, 3 goes to 1. And these different ways of writing that are just different starting points. Start the loop here, start the loop there, start the loop there, right? And then these just correspond to really the same loop, but with the arrows reversed, right? So you kind of think maybe that this and that, if you compose them, you get the identity. All right, well, we'll get to that kind of thing shortly. Here's some more. So just to complete the thought, the cycle notation for this one is 1, 3, because 2, and here's another thing. With a cycle notation, we only write the numbers which are moved. So if something's fixed, we don't need to write it, because it's fixed, who cares? I mean, it's just 2 goes to 2, yay. So we don't need to write that down. What's interesting is what's moved. And so 1 and 3 are moved. So we write this 2 cycle 1, 3 for that. This one, 3 is fixed. 1 and 2 are moved, so we just write 1, 2. And in this one, 1 is fixed, and 2 and 3 are moved, so we write 2, 3. So in total, S3 has 6 permutations. It has this 3 cycle, that 3 cycle, these 3 2 cycles, and then also the identity map. Which, well, how do you write the identity map in cycle notation? Well, it depends on what book you're reading, I guess. Sometimes I've seen people use like just an epsilon, like a variable epsilon for this. Like sometimes, and maybe I'll do that this semester. I have trouble making my mind, but sometimes people use that for that. Sometimes people might just do something like this if they just need to write something. But anyway, that's the identity. So that's kind of a special case. All right, moving on. Sorry, I'll pick up the pace here. I do have things to tell you today. All right, again, there's ambiguity with the cycle notation. 1, 3 is 3, 1, 1, 2 is 2, 1, 2, 3 is 3, 2. In the cycle notation, oh, I made up my mind over here. I'd say it is equal to 1, right? Let's see how group multiplication. I don't know what am I even talking about? We haven't defined a group yet, right? So probably, if I'm going to be a good citizen of the mathematical world, I should probably say something like, let's see how composition of bijections on n sub n. N sub n is my stupid notation for 1 through n. Let's see how composition of bijections on n through n sub n works in cycle notation. There we go. Whatever that word group means, we'll figure out next lecture, all right? So, also known as first day of class, but anyway, just saying. So in cycle notation, if I multiply 2, 1 times 2, 3, I get 1, 2, 3. Or if I multiply 3, 1 times 3, 2, I get 1, 3, 2. How's that work? Let's work it out, all right? So to see that this is equal to that, let's start with the number 1. Take 1, and you put it, and so the way these work, we have to read right to left. So I put 1 into 2, 3, nothing happens. I put 1 into here, 1 goes to 2. So we've established that 1 goes to 2. Then let's put in 2. 2 goes to 3, 3 goes nowhere. So apparently 2 goes to 3. Now we try 3. Well, 3 goes to 2, and then 2 goes to 1. So we've established that 3 goes to 1. Oh, we're back where we started. So we see that these two cycles multiply to give us this 3 cycle 1, 2, 3. And a similar argument will show you that that's the case there. So here's some more products, and so you can see if you can understand these, and we can talk about them office hours or something if you don't. Let's try another one here. Let's try to fill in a blank here that I haven't already filled in, and I'll try to just go through it real slow with you. Let's try to multiply. Let's try to fill in the blank right here. That looks like as good as one as I need to do. So this is a multiplication table, sometimes called the Cayley table. And so what we're going to try to do is we're going to try to compose 1, 3, 2 with 1, 3. All right. So the question is what was that equal? All right. And here I'm going to show you real slow here how that works. So I start. You pick a number, any number. But we're working with S3, so you better pick a number 1, 2, or 3. Actually, them's your choices. Let me scooch this up a bit here, make sure it's actually where you can see it. I always hate to do this sort of thing, then find out I was talking off the edge of the world. All right, so we start with 1, since, why not? And then, then I feed 1 into the given thing. So 1 goes to 3, right? Then that 3 gets fed into this one. 3 goes to 2. So, in fact, 1 goes to 2. Then I have to come back here and see where 2 goes. I plug in 2. 2 does what here? Well, 2 is fixed by 1, 3. It doesn't go anywhere. Then I plug in 2 here. So that 2 goes back to 1 again. Oh, well, what do you know? We're back to 1 again. So that closes this off, right? And then, actually, I know what's already going to happen. right? In fact, that's going to be it. But let's see what happens to 3. We put 3. 3 goes to 1. Come over here, 1 goes to 3. So 3 goes to 3. So if we wanted to be, you know, we could write that. But it's customary, since 3 is, you know, not moved, it's not interesting, it's fixed. Well, that's probably a wrong thing to say. It's not interesting. 3 is terribly interesting, right? 3 is a crowd. That's about all I got. So here's the 1, 2. I'm sure 3 is something. Oh yes, the Trinity, of course. What's wrong with me? Forget where I'm teaching. All right. Let's see here. So 1, 2, yes, is what we get right there. And so you might notice something about this multiplication table. There's no repeats. It's kind of neat, right? This, and this. These are distinct, and that pattern should play out as you calculate this. You should see that each row, ignoring the label rows, okay? So if we just look at below, like this part, if we were to fill this out, each row and each column should have just one copy of each permutation as you go across, either left or right or up and down. So if you want to fill in the rest of these, that's something you can use to make sure that you're doing it right. All right? Okay. So I've already been using this this terminology a little bit, but let me just fess up. I have been a naughty professor. I have not defined something. I was using the word. What is an R cycle? Here it is defined. Suppose we have a permutation, alpha, and it moves, it says alpha of aj is equal to aj plus 1 for j equals to 1 through r. And of course, to be clear, I'm assuming that the a sub j's are distinct. All right. And I think I'm assuming a sub j's are, I think I'm assuming the different a's are distinct here. All right. For j equals to 1 through r, alpha, and alpha fixes all x in 1 through n, for which x is not equal to a sub j. All right, for one of these a's. All right. So in other words, what I'm trying to say here is that this alpha moves. It moves a1, a2, dot 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 dot, a sub. Let's see if I can do my counting. A sub r, right? And so it moves all of these, right? But anything that's not in this list, it fixes, all right? Then this is what's called an R cycle, okay? And we denote it like that, alpha equal to that. So, you know, logically, the a sub r plus 1 has to be somewhere in here. All right, because otherwise, since it's a bijection, it would follow that, you know, if a moves to b, right, then I'm assuming if alpha of a is equal to b, then well, let me go on here. I'm about to chase a rabbit here. Let me move along here. All right, so there's a picture to illustrate this cycle corresponds to that diagram. It's example 1.37 shows you how we could calculate. I mean, I'm just verifying. Oh, this actually is a motivating example. I should probably use it because it motivates, right? So notice the thing about alpha and beta here is alpha is 1, 2, 3, beta is 4, 5, 6. So you notice that the numbers 1, 2, 3, and 4, 5, 6 are not overlapping, right? And looks like we've now moved on to looking at permutations on 6 symbols because it's, well, we need a bigger example to appreciate what we're saying. So this alpha moves 1, 2, 3, and it fixes 4, 5, 6. This beta moves 4, 5, and 6, but it fixes 1, 2, and 3. And if you go through this calculation right here, right, notice that alpha of beta of I is equal to alpha of I. Why is that? Because this is for I equals to 1, 2, 3, right? For those I, for those particular, oh no, hey, stop, sorry. For these I's, 1, 2, 3, that means that beta of I is equal to I. Why? Because beta fixes, it doesn't move 1, 2, or 3, right? So beta of I is equal to I. So alpha of beta of I is equal to alpha of I. And likewise, beta of alpha of I is equal to alpha I. Why? Because alpha of I is again a number in 1, 2, 3. And any 1, 2, or 3, beta does not move. So that means that beta of alpha I is equal to alpha I. On the other hand, beta fixes, oh, I'm sorry, this was since. I can't read my own writing. Since. Great. Already asked and answered. Moving on. I equals 4, 5, 6. We have a similar argument which says that alpha of beta of I is equal to beta of I, and beta of alpha I is equal to beta I. So if you look at what you got, we have shown that this is equal to that, and this is equal to that for I equals to 1, 2, 3, and also 4, 5, 6, which shows you that alpha composed with beta is equal to beta composed with alpha because they match on all their inputs, which is to say that this product of permutations is equal to that product of permutations. In other words, alpha and beta commute under function composition, which is kind of neat because function composition doesn't always commute, all right? And let's see here. So this times that is equal to that times that. I mean, there's another way you could do this example just by cycle calculation, I suppose, if you wanted, but that kind of begs a question which we haven't answered yet, so I'm going to not do that. All right. So that example we just looked at actually generalizes, all right? In fact, it can be shown generally, and that's what I do here, that if we have two cycles, all right, let me try to cover up some of this text so we can focus. If we have two cycles which have no common symbol, right, these are, if we have two cycles that have no common symbol, then by definition they're said to be disjoint, all right? These are disjoint cycles. Disjoint, all right? Disjoint, not this joint, disjoint. All right, there we go. And by essentially the same argument that I just went through half of, you can prove that those commute because one fixes everything in the other and vice versa. And then, well, here's the arguments in this paragraph basically, but in short, if we look at alpha, I mean, there's three things to look at. If you think about alpha composed with beta, right, of x, we can prove that that's equal to beta composed with alpha of x for all x. So there's three different kinds of x's to think about. There's the x's which are in neither one of these lists. And if x is in neither one of these lists, then x is fixed by both alpha and beta, and it follows immediately that both of these are equal, right? Because if beta of x is equal to x and alpha of x is equal to x, then this simplifies to x, and if alpha of x is equal to x, then we get beta of x, which is x, and x equals to x, yay. So of course what's more interesting is when x is actually taken from one of these lists, and that's what is described down here, right? So like if we think about x equal to bi, one of these guys, then alpha of bi is equal to bi, and beta, on the other hand, beta of ai is equal to ai. So we have, you know, they fix their complementary symbols because we're assuming they're disjoint. And on the other hand, of course, their image is still in the cycle, right? So like alpha of ai has to be one of these guys, and so it follows then that for example, beta of alpha of ai is equal to alpha of ai. And conversely, where is it? I've lost my place. So this is taking x equal to ai, right? So x equal to AI, we've calculated beta of alpha of AI, and we've shown it's alpha I. So I would like to show that that's, I'm sorry, I should just read the paragraph carefully and that would do it. I'm just trying to, well, I guess confuse you. Sorry about that. Let's see here. Oh, I guess I, idiot. Let's see here, where were we? Beta of alpha of AI is alpha of AI, right? So I've talked about that. Why is alpha of beta of AI equal to alpha of AI? You know, why is this true? Let's think through that for a second. Well, beta of AI is what? It's AI again. So this is alpha of AI. So they meet in the middle. This is equal to that, right? And similar arguments show you that when we act on BI, we get agreement in the middle at beta of BI. So this shows you that alpha composed with beta is equal to beta composed with alpha whenever we, I mean, for any input. If we feed it any input, we get equality. So since it matches all possible inputs, it follows that they commute. All right, so that gives us this theorem, which we should remember. And by the way, I mean, I do think that thing we were just going through is something you probably could prove on a test, if I asked you, right? The main difficulty in proving something like that is you have to really be clear about what your notation means, and but really there's not much to that proof. It's just trouble keeping track of what I was talking about, right? But anyway, this is an easy enough theorem to remember. Disjoint cycles commute. So now, not every permutation is a cycle, though. All right, some permutations are products of cycles. We here's one. If we look at this, where is this? Where is its home? Well, it's got 1, 2, 3, 4, 5. This is an S7, right? It's symmetric group on 7 symbols. And 1 goes to 3, 3 goes to 7, 7 goes to 1. So if you look at in array notation, this, and this, those give you that cycle. The 2 being fixed gives you this, which we don't usually write. The 4 and 5, they loop back on each other. That gives you this, which is called the transposition. And then, of course, the 6 on its lonesome here gives you that. We get rid of the 2 and the 6, and we just write that. So alpha is, in fact, the product of this 3 cycle 1, 3, 7, and 2 cycle 4, 5. Now, these are disjoint cycles, aren't they? 1, 3, 7, and 4, 5 are disjoint. So by the theorem above, you say, well, I could have also written that 4, 5, 1, 3, 7. That is true. We could have done that. All right. Now, there are various resources on the web for your, as you're getting used to cycle calculation. You know, it's nice to have something to check your answer, but beware, there are different conventions in different books. Some people have the cycles set up to go the opposite way. Now, I don't want to talk about that. I'm just saying beware. So, you know, when you look at a website, both eyes open, make sure it's actually doing things the way we're doing them. I have actually some links in the actual notes, right? Not the paper version, but the electronic one. All right, so let's continue this discussion here. Consider this permutation. Goodness, now we're on to S9. If we write this in cycle notation, 8 and 6 are fixed, and it looks like everything else is on the move. 1 goes to 4, 4 goes to 9, 9 goes to 2, 2 goes to 5, 5 goes to 1. Oh, that's a 1, 4, 9, 2, 5 cycle. And then 3 goes to 7, 7 goes to 3. That gives us a 2 cycle. And so we have alpha is equal to that times that, right? And we could also look at this permutation in terms of the subsets of S9 which are fixed, right? So we could talk, I mean, I've talked about elements being fixed, right? So my point is we could also talk about subsets being fixed. It has the same meaning, right? Like alpha of u equal to u, like the image of u under alpha equals to u. That would mean that u is fixed by alpha. All right. So just a more notation there. So anyway, that example that I was just looking at helps. In fact, you're maybe starting to suspect this. each permutation, all right, each permutation in Sn can be expressed as a product of disjoint cycles. All right. So let's walk through the proof of that. And so the proof is, of course, in part based on cycle notation. Let's pick a permutation in Sn. All right, step 1. Suppose A1 is the smallest element moved by alpha, right? Well, if no such A1 exists, then alpha fixes every element, and that means that alpha is the identity. Otherwise, we have that alpha of A1 is equal to A2, where A1 and A2 are distinct. Now, if alpha of A2 is A1, then we note that J equals 2, and we go to step 2. All right? I mean, saying that alpha 2 is equal to A1, that means that it's closed to the cycle, right? It's actually a 2 cycle. But anyway, moving on. However, if alpha of A2 is not equal to A1, then we define alpha of A2 equal to A3, right? Where A2 and A3 are distinct. And then we continue to define alpha of AI equal to A plus 1 until either we exhaust the set n sub n and find that alpha of aj is equal to A1 for some j greater than 1, all right? Notice that we cannot have a sub j equal to a sub I for some I greater than 1, because that would imply that we have aj maps to ai and ai minus 1 maps to ai, and that contradicts the fact that alpha is a bijection, which means that it's 1 to 1, right? So then that moves us on to step 2. So we let B1 be the smallest element which is moved in the complement. So basically we're taking the symbols 1 through n, removing the ones that were moved by the by alpha already in the A cycle, let's say. And so if B1 does not exist, then that means that alpha moves these and nothing else, right? Otherwise, we basically just go through the same thing and say, okay, well, you take bi plus 1 to be alpha of bi, and eventually there must exist a k such that alpha of bk is equal to b1, just as in the previous argument, and that gives us the A cycle times the B cycle, and then we just continue doing this, each time collecting everything that's moved, little buckets which are moved from 1 to the, basically we collect integers which are numbers from 1 through n rather. They are integers, fine, but no negative numbers in these lists, okay? Because we're looking at permutations on 1 through n. But anyway, we collect everything that moves from one to another, eventually has to loop back or exhaust everything. Once we're done with that, we move on. Either everything is fixed by that and there's nothing else, or there's more. And so B1 moves to B2, that moves to BK. BK eventually has to go back to B1, or this goes on to cover everything. And you've only got n numbers to work with here, so eventually you run out, right? You cannot have, and by construction these are disjoint, right? By construction these are disjoint. So this has to stop at some point, of course, because n sub n is finite, and so eventually we've covered all the alpha moved elements by a product of cycles in our current notation. It looks like that. And furthermore, by the construction, the cycles are disjoint. So I think this is a pretty good, I like this proof in some sense. It's not as rigorous as some you might find, but it's pretty rigorous, and it actually gives you an indication of how you actually do calculations with cycles, and so that's useful to me. If you'd like to see a more perhaps convincing mathy proof, you can look at Rotman, page 112 to 113, where he proves the theorem with an explicit induction. So next up is yet another fun fact about cycles. Each permutation in Sn can be expressed as a product of 2 cycles. That is, any element of Sn can be expressed as a product of transpositions. A transposition is a 2 cycle. So the second sentence is just a restatement of the first sentence in terms of lingo that you may not be familiar with yet. Transposition is just a 2 cycle. All right. So here, and in fact, pretty much, I'm going to ignore the text here and just focus in on this this calculation right here. All right, this is basically the key idea. We can rewrite this K cycle as this product of transpositions. Let's see why, right? Now what happens with A1? Let's start with A1. What happens with A1? A1 moves where? To A2, right? How about over here? A1, where's it go? A2. Okay. By the way, this is, you notice that there's A1, 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 right? Let's see if I can, let me put some numbers in here. It might help some of you. It'll help me. Don't get used to it. Don't get used to it. All right, so 1, 2, 3, 4. Let's rewrite it as a product of transpositions. So there's a 1, and the last one, 4. And then 1, and the next to last one, 3. 1, and the next to last one, 2. And that's it. All right. So I was just saying A1 goes to A2. So A2 is like this 2 here, right? That's the only place A2 appears in this whole list, because, so like A1 goes to A2, and then A2 is fixed, it's fixed, it's fixed, it's fixed. So A2 goes to, that's the end of it, right? So then where does A2 go? Well, A2 goes to A3, right? You look at this list, where does A2 go? Well, A2 goes to A1, right? But then the thing, it's not written here, but A1 goes to A3. And then everything to the left of that, A3, is just fixed by these guys, right? So we just got to A3, and then this goes on. Eventually you get to AK. AK goes to A1 on the left-hand side of this expression. How about over here? AK. AK is fixed, it's fixed, until you get to the leftmost transposition here, and AK goes to A1, just like it's supposed to. So these are equal on all of the inputs A1 through AK, and anything that's not in this list is fixed, so it stands to reason that these are equal. Again, that's not quite a proof, but I think that's a pretty good plausibility argument. I think that may actually be the proof, honestly. You know what? That's not really what this course is about necessarily. We really need to... we could spend weeks on this, all right, to really do it, to just beat it to death, but I want to move along here. So my apologies if I'm not living up to your expectations of rigor. All right, so actually, I'm not sorry. I'm not sorry at all. All right, I should shut up. Okay, so here's the thing I just wrote, except with 1, 2, 3, 4, 5. All right. On the other hand, any transposition multiplied by itself gets back to the identity, and also that means that it's not unique, right? So like if you look at 1, 2, 3, 4, 5 is 1, 5, 1, 4, 1, 3, 1, 2, but it's also 1, 5, 1, 4, 2, 3, 2, 3, 1, 3, 1, 2, right? Because you can stick in any product of a transposition in itself in this silly way, because that's just identity and it doesn't change anything. So the decomposition of a cycle into the product of transpositions is by no means unique. I think you can see that the decomposition of a cycle into decomposition of a permutation into disjoint cycles is closer to being unique, which is why if I ask a question on a test or something, I'll often ask for the disjoint cycle decomposition of the permutation, because I don't want to have to think about whether or not the crazy thing you wrote is equivalent to the answer that I'm looking for. In other words, simplifying my answer here often amounts to writing the disjoint cycle decomposition for the permutation. Now there's other things. If A, B, and C, and D are distinct, then of course the permutations commute. Here's some other, let's see here. These are, credit should be given where credit is due, I'm sure my brother would probably argue that these are in fact rigorous, and he's probably right. So any lack of rigor probably mostly stems from my inability to communicate them to you. But I'm on the clock here. I'm trying to get through this at a certain amount of time. So I dare not belabor these points too deeply. But anyway, thanks to Bill for providing a lot of this. It's from a handout he had in his abstract algebra course. And Anyway, so here's some other manipulations you can do with transpositions. What's happening here? We start with BC, AB, and we go to CA, CB. So what happened with the B's did what? I don't know how to say that. It says multiply out and cyclically permute trick. Oh, I understand that. You said you multiply this, you get that, and then this is equal to that. That's the cyclically permute. And then go back to the, oh, right, the first, last, first, middle trick. Anyway, so this is equal to that, this is equal to that. You can also derive this and that. So these are all handy-dandy permutation transposition tricks. And here's another example of some of these things, right? Anyway, here's the conjecture. If a two-cycle decomposition of a permutation has an even number of transpositions, then any other decomposition also has an even number of transpositions. Likewise, if a permutation permits a decomposition into an odd number of two cycles, then any other decomposition will also have an odd number of two cycles. You can see that in some of these identities, right? 1, then 3, 1, then 3. Started with 2, ended with 2, started with 2, ended with 2. If we go back to the previous page, you might have noticed that in this example as well, when you insert one of these, it changes the net number of transpositions by 2, which means if it was odd before, it's odd afterwards. If it's even before, it's even afterwards. Like started with 4, ended with 6, right? So it seems like the number of transpositions in a two-cycle decomposition of a permutation, it stays even or odd. That's the conjecture. Now the proof is actually kind of neat. I'll try to at least sketch it here for you. And it basically rests on this lemma. And the lemma is this: the identity permutation is written as a product of transpositions, right? Well, if the identity permutation is written as a product of transpositions, then the number of transpositions in the decomposition is even, all right? All right, first of all, it can be written as a product of even number permutations, because we can write 1 as 1, 2, 1, 2. That's always possible for n greater than or equal to 2. There it is. Now let's suppose we have some other decomposition of 1 into a product of 2 cycles, all right? Then we want to show that there must be an even number of these transpositions. And so he looks at these 4 different cases, all right? 4 different cases. And what he argues is that, let's see here. I was hoping not to get into the details here. All right. 4 cases of interest. A, B, C, D be distinct elements of the set 1 through n. Disjoint cycles commute. Let's see here. You can push them around like that. You can push that around like that. AB is 1. All right, fine. With you there. He says, notice in the first 3 cases, curses. In the first 3, I'll get it eventually. In the first 3 cases, sorry. In the first 3, I'll get it eventually. First 3 cases, 1, 2, 3, we can move A to the left. A moves to the left, yes. A moves to the left. Oh, that can be rewritten, right, as ACCB. So we can move A to the left. This one, A is already on the left, right? And then in the last case, A is canceled out completely. He says, so suppose A is the largest number appearing in all the transpositions, right? And so he says we can take the rightmost occurrence of A and move it to the left. And as we move all the A's to the left, at some point the A's must cancel out. because we have to end up with the AB-AB case, because if not, then it wouldn't be the identity permutation, right? Therefore, we can get rid of all the occurrences of A by canceling out the transpositions in pairs. It has to eventually come back down to that. And so if this has to cancel down to the identity by canceling out things in pairs, it must be that there's an even number of them, because otherwise you'd have one left over and it wouldn't be the identity. So therefore, the identity has to be even. Now once you know that, it's relatively easy to prove that any permutation has to be even or odd. In other words, that saying a permutation is even or odd makes sense, even though the number of permutations is not unique. It's unique up to even or oddness, all right? Like, so if I have a permutation and it can be written as product of 7 2-cycles, then any other decomposition of it into 2 cycles, it's going to have an odd number as well, all right? And so here's, I like this argument, I think is neat. Every permutation in Sn is either even or odd, so pick a permutation. By the transposition trick, we can rewrite it as a product of transpositions, right? You just take each one of the disjoint cycles and write it as a product of transpositions. But anyway, suppose you had 2 different decompositions of the permutation into a product of transpositions. Then, let's see here, 1 is equal to sigma sigma inverse. And this will prove, so I guess I'm getting a little bit ahead of myself, but well, maybe not. I mean, in Math 200, you perhaps learned that the inverse of a function is what? It's the, the inverse of a composite is the composite of the inverses in the opposite order, so that's what we're using here, right? So like the inverse of this function is, this is a composition of that function and all the way out to that function. There's actually k of them, I suppose. So by the sock shoes rule for a composition of functions, inverse of composition of functions, we have that, and that. And then, but on the other hand, these are 2 cycles, transpositions, so their inverse is easy enough to write down. You just, well, they are their own inverse. It's kind of dumb. So you have that, right? So we've written 1 as a product of these 2 different transposition decompositions for the permutation, and so it is as a product of L plus K transposition, because there's L of them here, or rather L of them here, and then K of them here, so L plus K transpositions. And our lemma says that L plus K must be even. So what's that say? It says either both L and K are even, or they're both odd, right? We can't have L even and K odd, because then L plus K would be odd, or vice versa, right? So then that means that if that's even decomposition, that's an even decomposition. That's an odd decomposition, then that's an odd decomposition. So it makes sense to say that permutation's even or odd, which is pretty neat. All right, so I'll let you read these comments here. You can also define the sign of a permutation. It's defined to be 1 if it's an even permutation, -1 if it's odd. You can prove, this is just a, by the way, this is just a notation for that. It's kind of funny notation. You can corollary 1.38, which I think I just skipped over, says that the sign of a composition of 2 permutations is the product of the signs. A fact that we'll come back to again. So among other things, so like an even times an even's an even composed with an odd's an odd composed with an even is an odd composed with odd, of course, is even in this world. And it's kind of neat. One of the applications for permutations, by the way, guys, is that you can write the formula for the determinant in terms of sum over permutations on n symbols, and then this puts the proper plus minus into the determinant formula. And these are the entries of your n by n matrix. For example, here's how it works out for the 2 by 2 case. Going back to S2, which had just in cycle notation 1 or 1, 2, And so you work it out, you get A11, A22 minus A12, A21, which, hey, I'm going to add some value here for you. That's the determinant of this guy, right? You're like, thanks for writing that out. There's tons of other things in this talk I didn't understand, but you're taking time to write this. Good job. Yes, I am. Haha. Anyway, so yeah, so we can write the formula for a determinant using permutations rather beautifully. A couple other small sundry facts I'll share with you here. The inverse of a k-cycle is pretty easy. You just take the cycle, write it in the reverse order. It's easy to verify that that is in fact the inverse in the sense of function composition of that. That's very, very neat. This is a slightly more technical result, which we will more or less prove in other contexts as we go on. So, in fact, this argument here is one you'll see. I'm sure it's going to come up. Maybe not with this idea, not notation, this example, but the same calculation. It's going to come up. So it's worth reading through this kind of carefully for yourself. If a permutation is formed by a product of disjoint cycles, then the order of the permutation is the least common multiple of the lengths of the disjoint cycle. By the way, what this means, order, it's the, if you can take the permutation, so if like alpha to the, let's say r is equal to the identity, and that's the first r which that happens, no smaller power of r happens, then alpha is said to have order r, all right? So the order of a 2 cycle is 2, the order of a 3 cycle is 3, the order of a 4 cycle is 4, and so forth. So what this paragraph here says is if we take sigma and it's a product of these k disjoint cycles, then, and I'm supposing that the order of the cycles are m1 through mk, so my m1 would be analogous to the r I wrote here if gamma 1 is like alpha. Then you can prove that the product of more than 2 disjoint cycles still commutes, and so if you calculate the nth power of that product, since it commutes, this simplifies to just gamma 1 to the n. I can move the gamma 1s all together and get gamma 1 to the n. I can move the gamma 2s all together and get gamma 2 to the n. I can move the gamma k's all together and get gamma k to the n because these commute, all right? And so if we let n be the least common multiple of m1 through mk, then that means every one of these is raised to some multiple of the power which makes it go to the identity, and it follows that this whole thing is in fact the sigma to the n, is in fact sigma to the m, where m is the LCM there, is equal to 1. So that shows that the order of sigma is at most m, but then you still need to show that the order of sigma is really m. You have to show that there's no smaller power for which sigma to the sigma to the n is equal to 1. Like m is the first power for which sigma to the m is 1. And so contradiction is probably a good tool to use here. Suppose that there was a smaller power, j less than m, for which sigma j to 1. By the calculation we just went through, that means that gamma I to the j is equal to 1 for j equals to 1 through k, which means that m1 divides j for each 1 through k. What's m1? I'm sorry, lost track. My eyes. I don't know what this m1 is. I'm sorry, I missed where I introduced that. Maybe that's a... Sorry. Hence j is a common multiple of m1 through mk, and j is less than the least common multiple, which is impossible, right? I think that may be a spurious typo. Let's see here, by calculation above, gamma I. Hence, oh, you know what that is? That's supposed to be an m sub I. That would make way more sense. So if this is equal to 1, that means that it must be, j must be a multiple of mi, because mi is the least power for which gamma I raised to the mi gives you back the identity. So yeah. Let's see here. Hence j is a common multiple, and it's smaller than the least common multiple, which of course is a contradiction. And it follows that no smaller power of sigma can give you the identity. M is the first power for which it happens, and therefore that's the order. All right. Well, anyway, so that's a nice identity. Apparently due to Ruffini. Let's see here. And finally, this is just some example, some calculations. If alpha is 1, 2, 3, 4, beta is 1, 7, 4, then alpha inverse is 4, 3, 2, 1. Beta inverse is 4, 7, 1. This is the order of alpha. Order of alpha is 4. The order of beta is 3. These are not disjoint. Notice that they have a common 4. 4 is moved by both of these, so they're not disjoint. But we can still use basic function inverse stuff, right? So like the inverse of the composite of two functions is the composition of their inverses in opposite order, which is, by the way, 4, 7, 1 times 4, 3, 2, 1, right? And let's see here. Then those can be, I multiply those out using what we talked about earlier, right? Start with 1, 1 goes where? Oh, sorry, 1 goes where? 1 goes to 4. 4 goes where? 4 goes to 7. 1 goes to 7. Where's 7? What happens with 7? 7 goes nowhere. 7 goes to 1. So that closes the 1 cycle. 2 cycle, 1, 7. Then we go into 2. What happens with 2? 2 goes to 1. 1 goes to 4. So 2 goes to 4. 4. What happens with 4? 4 goes to 3. 3 goes nowhere. What happens with 3? 3 goes to 2. Right? What happens to 2? 2 goes nowhere. Oh, 3 goes to 2. That closes that 3 cycle. So this sigma inverse can be written as 1, 7, 2, 4, 3. And the lemma that I just did a bad job of proving, because it would take longer for you guys at the moment, and we will go through that proof in another example, so don't worry too much about the thing that I didn't make sense of just a minute ago. Sorry about that. At the moment I just want you to be aware of this result so you can use this in your homework, alright? That the order of a permutation, which is written as the product of disjoint cycles, it's the least common multiple of the orders of the disjoint cycle. So like this has order 6 because 2, 3, least common multiple, 2 and 3 is 6, right? By the way, the order of an element is equal to the order of its inverse. This is something I think I've asked you to prove in the homework, all right, carefully. Certainly more careful than I was being a couple minutes ago. Sorry about that. But anyway, so I hope that gets you started. I've given you some homework to try to hone your skills on cycle notation, and this is an important example for us. We'll keep coming back to permutations. There are permutations and Zn. Two of our major examples. We'll do a lot with those two examples, but of course also there are many other examples of groups which have nothing particularly to do with these two. So anyway, sorry I went a little bit over time. But I think I said nothing in at least 20 minutes of this, so it really was only 40 minutes. Anyway, thanks guys, bye.